Hi all, let's continue with the next topic of microprogram example part 2 of unit 2. So in this lecture we are going to discuss about what is a symbolic microinstruction and its format and an example of a fetch routine, example of a microprogram for a fetch routine of an instruction cycle. So coming to a symbolic microinstruction, so each line of your assembly language program, it defines a symbolic microinstruction. So a symbolic microprogram, it can be translated into a binary equivalent by means of an assembler. So a symbolic microinstruction, it contains mainly 5 fields as we have already discussed in the previous lecture. The label field, micro operations field, CD field, BR field and AD field. So each symbolic microinstruction is divided into 5 fields. Label, micro operations, CD, BR and AD. CD represents a condition, BR represents branch and AD represents the address. So coming to a label field, it can be empty, you can have it as empty or you have to specify a specific address which is terminated by a colon. And a micro operations field, when we have already seen the list of micro operations, which are F1, F2, F3. So that is specified in case of a micro operations field, which are separated by commas. Next is the CD, condition field. So we have already seen the condition field, which can take, which is a 2-bit field, which can take either 00, 01, 10 or 11. So based on the condition that you are specifying, the condition field can be either U, I, S or Z. Next is a BR field, branch field. It may contain one or more 4 symbols. So in the branch, also there are 4 possibilities for 0001, 1011. So any of these can be specified as a BR field. And finally, we have an address field. So address field specifies the value of address of the micro instruction. It can be anything. It can be symbolic address where we must appear, which appears as a label, or if you can specify the address of the with the symbol next. If you are giving next, it means that next is nothing but you have to execute the next instruction according to the program order. And when you are giving a branch instruction, the return address has to be specified or map symbol. So address field is left empty. If it is left empty, it has to be converted to 7 zeros. In case of a mapping, you have to leave it with 7 zeros. So we'll see an example for a fetch routine. So the control memory, as we already know, it is of 128 locations are present in the control memory. When you see the diagram, we have seen that the size of a control memory is 128 into 20, which means it is divided into 128 locations of 20 bits each. So out of the 128 locations, the first 64 locations of your control memory are occupied by 16 instructions. So we have already seen the instruction format where the instruction format opcode is of 4 bits, right? When the opcode is of a 4-bit opcode, there are 2 to the power of 4 possible instructions or operations that can be performed. So to the power of 4 in the sense 16 operations, 16 instructions. So these 16 instructions are occupied by the addresses 0 to 63 of the control memory. So whatever routines or whatever code that is required for executing these 16 instructions, they are stored in the control memory at addresses 0 to 63. So our fetch routine, when you are fetching an instruction cycle starts with fetch, decode, execute. Now we'll just see an example of how a fetch routine microprogram is written for a fetch routine in the control memory. So the fetch routine will start at an address location 64. So the instruction which has to be executed for the fetch routine will be stored at a location 64 of control memory. So it requires 3 instructions. So it requires 3 addresses of the control memory 64, 65, 66. Because our fetch routine contains 3 instructions, so it requires 3 locations of the control memory from 64 to 66. So if you look at this, this is just the whatever is there in your fetch cycle of the fetch routine of the instruction cycle, whatever we have seen in unit 1. So the fetch contains mainly three micro instructions. In the first case, whatever is initially the address, it will be loaded into the program counter. So whatever address is present in the program counter, that has to be first loaded into the address register before the particular address is fetched. So next, whatever is address present in the address register, for that particular address of the memory, the instruction is being fetched and it is copied into the data register. Or rather than instruction register, we are using a data register. So the instruction is copied into the data register and program counter is incremented by 1. So that the program counter now points to the address of the next instruction. Next, you need to decode that particular instruction. So here the decoding is done. So decoding is nothing but here you are mapping it based on the mapping. So 0 to 10 bits of the data register are moved into the address register. The address part is moved into the address register. So in the case of this, this is nothing but the mapping technique what we have seen in the address sequencing mechanism. So how you are mapping the control address register? The data register opcode bits of 11 to 14 are copied into the control address register bits of 2 to 5. So you are mapping your 4-bit opcode into a 7-bit address of the control address, 7-bit address of the control memory to find out where that particular instruction is stored in your control memory, right? So this mapping technique is done by copying the opcode bits of the data register into 2 to the 5 bits of the control address register, whereas the remaining bits of the control register are cleared to 0. So 0, 1, 1 and 6 bits are made as 0, where the remaining bits are copied as it is into the control address register. Now we will get the address of the control memory where the particular instruction is stored in the control memory. So for this particular fetch routine, we are converting it into a symbolic microprogram. So origin 64. So origin 64 basically means that it is a pseudo random instruction. ORG is a pseudo random instruction which defines the origin or a first address. So the first address of the particular fetch routine is 64. So symbol ORG64, which is nothing but it informs the assembler to place the next micro instruction in the control memory at a decimal address 64. So which is a binary equivalent. This is a binary equivalent of 64. Okay. So first we'll start the program with origin 64 because our program is starting at a 64th location of control memory. So this micro instruction contains 5 fields: label field, micro operation field, condition, branch, and address. So since we are starting at a location 64 of the control memory, it is labeled as 64. So the label field is fetch. We are labeling it as fetch with a colon. So next is the PC to AR. So if you look at this particular table, so PC to AR. So this is PC to AR. The symbol is PCTAR. So that is mentioned here, PCTAR. So we are not looking at any condition here. So we have to mention 00, which is U. And when you are giving U unconditional jump, it is you have to mention it as jump and next. So in this case, it has to execute the next instruction according to the program order. Next, coming to next instruction, which is stored at 65 location of the control memory. We are not giving any label here. So here M of ER to DR. So this is you are reading the contents of the memory. So for that, so if you look at this read M of ER to DR, which is specified as a symbol read. And similarly, you are incrementing your program counter by 1. PC implies PC plus 1. So that is INC PC. So those two symbols have to be mentioned, read comma INC PC. And here also no condition you are checking. So you jump and it has to next means it has to go to the next instruction according to the program order. So the next instruction stored at location 66 of the control memory. We are not giving any label. So DR to AR. DR to AR. So DRTAR, that is mentioned here, unconditional jump, and this is your mapping. So you have to specify it as map. So whenever you are specifying it as map, as you have seen here, the address field will be left empty and it is converted to 7 zeros by the assembler. So instead of here the 7 zeros, the address field will be left empty. So if you see the particular binary microprogram, you are just converting the symbols into the binary values. So if you look at this binary addresses, 64 is represented in a binary format like this, 65 and 66. So F1, F2, F3. So where is this function PC2AR stored? That is stored in F1 function, which is number is 110. So 110. So here we have 110 for F1, where the remaining will be zeros. And in case of CD, unconditional branch, so according to this table, unconditional branch means 00. So we are specifying it as 00. And BR is also 00. And address, you are giving next. So next instruction according to the program order is 65. So this 65 address is mentioned here. And next, here also this instruction is present in F3 function, F3 micro table. So it is represented by binary number 101. Here also we are giving unconditional unconditioned. So we are specifying at 00. And here also we gave next. So it points to the address of the next instruction, which is 66. So here this particular function, it is stored at F1 table. So with a number binary value 101 that is given here. Here we are giving as map. So map is present as the BR symbol 11. So here 11 is specified here. So whenever you are giving a map, the address will be here, the next address table will be empty and you are specifying it with 7 zeros. So which point to a 0th location of your control memory, where some mapping will be done. So this is how you convert your this particular instructions, micro instructions, into a symbolic microprogram, and the symbolic microprogram is again converted by an assembler into a binary equivalent program. So this is just an example of the fetch routine of an instruction cycle. Similarly, decode, execute all the phases of your instruction cycle will be converted into your symbolic microprogram and then converted into your binary microprogram. So this is an example of a microprogram. Thank you.